Well, thank you to Vijay and Prashant for inviting me. I mean, I think it's an honor to be here again at COMSNET. And thank you all for coming. I know it's early in the morning, first session of the conference, I guess. So I will talk about some work that some colleagues and I are doing on improving road safety using low-cost devices, in particular using a smartphone. Right? Normally, you think of a smartphone as distracting people and causing safety issues. We want to see how we can use a phone to actually improve safety. And the project is called Harnessing Automobiles for Safety, and you'll understand why. And this joint book is a bunch of people. Akshay Nambi, who's a member of the PC of this conference, is a key member of the team, and there are a bunch of others involved as well. So the motivation for the problem, I think this audience probably doesn't require too much of a context here, but road safety is a big issue in this country, and not just this country, the world over. If you look at the chart on the right, it's listing the top causes of death around the world. And road injury and road accidents are in the top 10, like I think 8th or 9th of the list, right? So it's a huge problem, especially if you look at younger people, it's in the top 2 or 3 causes, right? So it is something that you can think of as a public health issue as well. Now, if you think about the problem of road safety, there are largely 3 factors that play a role. There is the vehicle, the driver, and the infrastructure. And the issue is that none of these 3 actually is being monitored on an ongoing basis to sort of ensure safety. Now, in this talk and in our work, we are primarily focusing on the driver because, as I'll show in a couple of slides, a lot of the risk factors associated with accidents center on the driver. Occasionally, a pothole could kill someone, or a tire burst, or sort of a brake failure in a vehicle could cause an accident. But in the majority of cases, it's the driver and the driver's actions that cause issues. So what's our setup like? So basically, we want a low-cost system that can be deployed at scale. So as I said, we're going to work with just a smartphone that's mounted on the dashboard or on the windshield, just like that red circle there shows, in such a way that you have the front camera of the smartphone looking at the driver, the back camera looking out to the front, okay? And we also have a low-cost OBD devices, about 1,000 rupees or even less, that attaches to the vehicle and pulls out a bunch of engine parameters and other vehicle parameters. We're just gathering the data right now. We're not really using that in the work that I'm presenting today. So we created a setup like this and deployed this on about a dozen vehicles, Microsoft Office cabs, and we've gathered more than 25,000 kilometers of data on Bangalore roads. And just to put this work in context, right? So 10 years ago, soon after I moved from the US to Bangalore, my colleagues and I worked on a system called Nericel, which was perhaps one of the earliest smartphone-based traffic and road monitoring systems, right? And this was done at a time where the smartphone looked like this. It didn't really have any sensors. It had a microphone, I guess, but nothing else really. So even accelerometers had to be attached externally. So we built the system. We did a bunch of things. We wrote a paper which had significant academic impact, I would say, and also that kind of idea has taken off. There's a bunch of startups doing smartphone-based telematics, so for insurance and things like that. So the question is, okay, we did this 10 years ago, and a bunch of startups have happened. What's new, right? So if we think of systems like Nericel and a lot of the other systems out there, they're largely working with these 2 sources of data. There is GPS that tells you where the vehicle is, and there is also inertial sensors like the accelerometer, the gyroscope, and so on, that tell you about the motion of the vehicle, right? Things like road bumps and braking and so on. But what is missing in this picture? What I would argue is that from a safety viewpoint, what matters a lot is the driver and driving context, right? And I will explain that. So, this is a World Health Organization study that lists some of the top risk factors for road accidents, things like speeding, drinking and driving, and so on. As you see, many of these factors have to do with the driver, the state of the driver or the actions of the driver, right? So, something like distracted driving, where I don't know why it went upside down. Anyway, yeah. So yeah, the guy is not that distracted that he's like driving upside down, but he's talking on the phone, right? So it is something that an accelerometer or a gyroscope is not going to capture. You need to actually be able to sense the driver's state. You need to use a camera to look at the driver, right? That's an obvious way of doing it. An even simpler example is speeding, right? You might think, hey, speed is very easy. You can get it out of GPS, and okay, there's a speed limit. You're going faster than the speed limit, and so on. Is audio turned on in this? Audio is on, right? Okay. So now, this is actually from the airport road here. I was going to the airport early in the morning. I don't know if you can hear that. So it's saying something speed alert, please slow down. Okay. I don't know why the video is jerky. Maybe the laptop is. Yeah, the video, ignore the jerkiness, but there is this audio that plays, right? Now, when you talk to drivers, they find it very irritating because he says, look, the whole road in front of me is open. Everyone's going fast. I'm going at 85 kilometers an hour. The speed limit is 80. This thing is chiming, right? The point here is that from a safety viewpoint, yes, speed matters, but the context around which around you matters even more, right? If you are tailgating, or if you are zigzagging through traffic, if you are being aggressive in various ways, that is a much bigger deal than simply the fact that your speed is 85 compared to 80, right? So both from the context inside as well as outside, we believe it is important to know what's going on around a vehicle and inside a vehicle than this thing. So basically in HAMS, what we're doing that is new compared to our work from earlier and a lot of other work is we're using cameras that are available on all smartphones. One looking at the driver to understand the state of the driver, the other looking out to the front to understand the driving environment, right? And I'll just skip this. This is just a high-level picture. So in addition to driver monitoring, as I said, we can also do vehicle monitoring and infrastructure monitoring, like potholes and all those things. And we are doing a bit of work with this, mostly with collaborators, but our focus really is on the driver. So what kind of things are we doing with driving with regard to driver context? We're looking at things like fatigue, the signs of fatigue, yawning and eye closure and so on. We are looking at distraction, I already showed you in that video. And also we're looking at driver gaze, particularly for the purpose of tracking what's called mirror scanning, right? So mirror scanning is, a good driver is supposed to scan his or her mirrors to be aware of what's around them, to be situationally aware. You need to know what vehicles are to your left, what's to your right, what's behind you and so on, right? So that if you had to take some emergency action, you know what's behind you, right? Now, so therefore they should scan their mirrors, and that is something that a lot of drivers don't do. Now, with regard to driving context, I mentioned tailgating, so how far are you from the vehicle in front? That matters, right? So if you're going at 80, but you're only 10 meters behind the vehicle in front, that's very dangerous. If you're going at 20 kilometers an hour and you're 10 meters, that's fine, right? Relative speed, and also perhaps something that's uniquely Indian, which is wrong side driving, right? So you're driving, and this happens often in the highways where someone does not want to go 2 kilometers and do a U-turn and come back. They just go on the wrong side, right, on the edge of the road. Right? So I don't know why this is advancing by itself, but anyway. So what are we doing in the project, right? So there's 3 broad research thrusts. The first is that since we are looking at a low-cost solution that is retrofitted onto existing vehicles, we have to make it so that it is robust to this act of installing something after the fact, right? So let's say I put a smartphone and I turn it a little bit, tilt it a little bit. It should be able to auto-calibrate so that it doesn't expect a perfect mounting every time, right? Because things are not going to be perfect. We also are looking at sensor substitution. So we may not have all the sensors that we want. So can we use a different sensor, a low-cost sensor, as a substitute for a more expensive sensor, right? And finally, all of the processing, we are gathering a lot of video data and image data. You can't send it to the cloud. It's just too much work to do, and also from a privacy viewpoint, it's not something you would want to do. Therefore, we want to do all of the processing at the edge device itself, which in our case is a smartphone, right? So that's sort of what a lot of our research is around. But beyond the research, we have also been doing an actual deployment, working with Maruti Suzuki's IDTR. So I'll actually introduce this later, so let me not spend too much time on this, as part of a driver training program, right? So in this talk, I'm going to keep it short, so I'm going to just talk about 2 specific problems. One is driver gaze tracking, and the other is the vehicle ranging for tailgating, okay? So driver gaze tracking, I mean, where a driver is looking obviously is important for a number of reasons. I already talked about mirror scanning, but beyond that, things like rubber necking. Something interesting is going on the side of the road, and someone's driving like that. That's dangerous. Texting, where someone's looking down and driving because they're looking at their phone. All of these center around the driver's gaze not being where it should be, right? Now, to figure out the driver's gaze, you need to look at 2 things: the pose of the driver, the head pose, which way the head is pointed, and also the state of their eye, right? So because you might be looking straight and looking through the corner of your eye at the mirror, for example, right? So just to give you sort of a preview of what's to come, this is what we have built, right? Okay, I guess I will come back to this later. Later slide should have this. Yeah, I think in transferring the presentation to a new laptop, some things have happened. But what this was supposed to show is that what we have built right now is something that classifies a driver's gaze into 3 categories. Driver looking straight, looking to the left mirror, looking to the right mirror, right? And as I'll explain later, we can use just simple 3-state classification to detect instances where the driver is not doing the right thing. Is not sort of, for example, if someone remains looking straight for 20 seconds and they have not looked left or right, that's an indication of a driver who's not maintaining situational awareness. So, this is a high-level pipeline. You basically have to detect the face, and you extract what are called facial landmarks. I'll show a picture in the next slide. And then you estimate the head pose and the eye gaze, right? Now, what are the issues? Now, people have, of course, done gaze tracking in a lot of other contexts and so on, particularly for web conferencing. So let's say you're doing a conference with someone. You want to know which way the person is looking to improve the experience of the conferencing. So there are a few challenges in our context. The first is that the head and the eye movement is much more frequent in our context compared to, for example, an web conferencing setting, right? Because the driver is constantly sort of moving their head, shifting their eyes and so on. The second is the camera position is non-standard. So, typically in a web conference setting, the camera is in front of you and you're looking at it or close to that direction. Whereas in our context, the camera is off to the side, and if the camera were directly in front, you would cause an accident, right? You would be obstructing the view of the driver. So it is by sort of design off to the side. And lastly, as I mentioned earlier, there are a lot of variations with regard to the vehicle, the driver, and also the mounting of the camera. So if the driver is tall, he or she might be sitting back, and therefore the kind of angles they move their head would be different from a driver who is short and looking and sitting close to the steering column. Likewise, different vehicle geometries and so on, right? So all of this we need to deal with. So, facial landmarks is something that people in the vision community have worked on, and a standard model typically has 68 landmark points for a human face that various algorithms will detect. So we took existing algorithms and then we enhanced it both with regard to training it with additional data, and also for efficiency reasons, throwing away some of the 68 landmarks and reducing it to about 22 or something, because for our purposes that was sufficient, but it gave us some computational efficiency. So we could track fewer landmarks and be able to track the kind of gaze thing that we want to while consuming less CPU. Now, so we did that, and we took the, once you've identified the facial landmarks, you can estimate the pose of the face, okay? So we did that, and we took the yaw angle. So yaw is basically the angle as you turn your head left to right, right? And we tried to sort of cluster it. And what we found is that we found these clusters that are not well separated, right? So basically there are cases where you can't tell which way the driver is looking, just looking at the head. So we did two things. One is we filtered out transient head poses. So the point is that when someone's driving, as I said, they're constantly shifting their head. We don't really care about all those intermediate directions they may be looking at. We care about the directions where they actually persist, and also directions that they repeatedly visit. So your mirror is always there. So every 10 seconds you might briefly look at that. So that's a direction that repeats. We want to sort of identify those. And we also want to obviously look at things like straight, where you're looking sort of a significant length of time, right? So we took the yaw time series and identified these stable regions where the gaze was persisting. And then we also incorporated eye state. So in the chart I showed earlier, eye state was not incorporated. That was just looking at the head pose. Because of what I mentioned earlier, where the driver may not actually turn their head, they might actually just move their eyes. You have to look at eye state as well. So we basically took eye state as well. And we combined the head pose with eye state with a neural network to come up with a combined gaze of the driver, which combines both the pose of the head as well as the eye state, right? Now, once that is done, we could then also do auto calibration. So what then happens is, when a drive starts, you don't know what vehicle it is, you don't know exactly how your camera is mounted, you don't know how tall the driver is, and how far back from the steering they're sitting and so on. But you can learn all that. And the way that works is that in the first, say, minute or two of the driver, of the drive, let's say the driver actually shows the full range of movement. They look straight, they look to the left, they look to the right. We can, using the combined pose that you calculate here, you can actually cluster data, and you will find, this is data from our experiments. You find these 3 distinct clusters corresponding to the driver looking straight, looking to the right, and looking to the left. Right? And these 2 are less well separated because in a right-hand drive vehicle, the angle that needed to look at the right mirror is not as much as the turn required for the left mirror, right? But this is clustering, right? Unsupervised. So there's no training, there's no hand-holding here. We just sort of learn it by looking at a couple of minutes of drive data. Once that is done, we can then classify further frames as left, right, and straight, right? And we have experimented with this and seen that it actually works quite well. So, good, this video is working. So this is this thing in action. So essentially, you see, if you can see the red text here, it's classifying the driver state as straight, left, or right, as I mentioned. And these are the landmarks that are being tracked and so on, right? So, yeah, a particular application of this is for mirror scanning. So you can, look at how long it's been since the driver scanned their mirrors. And if it's been, more than 15, 20 seconds or whatever, you can decide the threshold. You can create an alert, right? Saying, okay, this driver is not scanned, right? So now, this is just a demo thing. We're not going to blare saying, look at your mirrors. But, from a driver training viewpoint, which I'll get to next, it's quite useful. So now you might wonder, okay, what happens at night time, where lighting is poor and you don't really see very much. Maybe there's audio in this. Okay, I don't know. So we are also working with thermal cameras, FLIR sensors. Now, these are not common in phones today, but just like accelerometers were not in phones 10 years ago, but appeared soon afterwards, we believe things like this would make an appearance, and so it makes sense to look at these. Today, the sensor is about $150 attached to the phone. Now, the second problem I'm going to talk about is with the camera looking out to the front, vehicle ranging, right? And as I mentioned earlier, from a safety viewpoint, it matters how much of a separation you're maintaining to the vehicle in front. There is what's called the 2-second rule, which says that at any point in time, the separation should be at least 2 seconds worth of distance that you would travel at your current speed, right? So you can do the calculation. I think at 60 kilometers an hour, it requires a separation of 30 meters or something, right? So now, obviously, people have self-driving cars and so on. They've worked with sensors like LiDAR and so on that give them a very detailed picture of all objects around and how far you are from everything. But that's expensive. In fact, we experiment with LiDAR. No, a single LiDAR sensor costs, I think, about $150, at least the one we purchased. And by itself, it's useless because it will shoot its laser, get a range. You don't know what it got the range with respect to, right? Where it's the vehicle in front, which part of that vehicle, you have no idea. So typically what people have is an array of LiDAR thing, and they actually mount it on something that sort of scans the environment, right? That contraption is now very expensive. Now we are talking about thousands of dollars, if not tens of thousands of dollars. So again, from a low cost viewpoint, we don't want to do that. We just want to use the camera. And so our approach is very simple conceptually. We use the camera view and identify bounding boxes around vehicles. It's an object detection problem, right? Which again, the deep learning community and the vision community has worked on. So once you have identified the bounding box around a vehicle in front, then if you can identify which vehicle it is, let's say you know this is a sedan or something. You know the sedan is roughly 1.5 meters wide. You know the size of the bounding box, therefore you can, through simple geometry, you can estimate the range, right? The issue, however, is that the state-of-the-art approaches, DNN-based approaches for identifying bounding boxes are very expensive, right? So we actually run them on a phone, and it takes about a second or sometimes even more to process a single frame, right? So that's going to keep it very, very slow. So to address this problem, we came up with a very simple hybrid approach, right? The idea here is that rather than run the DNN on every frame and detect bounding boxes afresh every frame, you leverage the fact that the set of vehicles you see from frame to frame is not going to change very much. So you could use traditional vision-based tracking, which are much more efficient to track vehicles from one frame to the next. And so this picture here shows at frame 700, we ran the YOLO network and found these bounding boxes. At frame 720 and 740, we just tracked those bounding boxes using a tracker, right? And you can see that it's still doing pretty well, right? And so we come with we have an adaptive algorithm where we decide when we should run the DNN again, right? So that gives us a lot of efficiency. So this, to me at least, is a bit like how MPEG coding works. You have your iframes, which are the full-blown sort of expensive frames that are independent of everything else, and then there are the P and B frames that are relative to these, right? So it's a bit like that. So you have these orange ones and then the cheaper blue ones interspersed. So this is how well it works. So we basically are looking at range with respect to a car in front and a motorbike on a drive. X-axis is frame number or time you can think of, and the range is changing. So the ground truth is shown as black, and red is our estimated range, right? And you can see that it tracks the black quite well. There are some portions where there is no red, and that's because our algorithm was not able to detect the bounding box, and so we were not able to do the range. But in many other cases, the red does track the black very well. So this is ranging in action. Actually, on the street right outside, it is there's a flyover coming, and this is just because our office is just 5 minutes from here. Yeah, I think Chancery Pavilion is probably the building there. Okay. Yeah. Yes. Oh, okay. Sorry, I just skipped over that. So basically, let's say that this is an Innova, or at least this is a large car, right? And let's say the width of the large car is 1.5 meters. In your image view, this is certain number of pixels. So simple geometry will allow you to calculate, and your camera's parameters, like angle of view or whatever, right? So you can just calculate how far it is. So yeah, so I'll just play it for 30 seconds. So we just did a drive where we had a vehicle of our own in front, and you will see that, occasionally it will latch onto some other object, bounding box detection or object detection rather is not perfect, but you can filter those out. So now the range has increased and so on. Okay. Yeah. So now, let's talk about applications or something like this, right? So let's say you have a system that can monitor drivers and their driving. What can you do with it? We believe there are a number of possibilities, right? The first is driver training. So that's an example I will talk about, so let me leave it at that. The second is licensing. So today, licensing is done in a way where there's a lot of failures, there's a lot of corruption and so on, right? So a human inspector is checking your driving, supposed to check your driving, and as a result, the process could be compromised in many ways. You could have a device like this, running a system like this, actually check how you're driving. And not just that, you can say that, today when you get a driver's license, essentially you have a license to drive, no one can check what you're doing after that. But with a system like this, you can say if you're getting a learner's license, for the next 30 days or the next 1,000 kilometers, you must have a device like this in your truck, or especially for commercial vehicles, your bus or your cab, and it needs to check how you're driving, and if you get a satisfactory report at the end of the month, then you will actually get a real license. And because we have a camera, we can also make sure it is the person who's who's got the learner's license that is driving, right? Beyond that, you can look at fleet management. So if you own 1,000 trucks or 100 cabs today, you have very few tools to know what's going on. You don't even know who's driving your truck. A system like this can help you keep track of what's going on, look at signs of fatigue, look at things that your driver is doing that could endanger both the driver and the cargo. Like some of these guys actually, it's kind of sad reality in India. You talk to them, they care more about the value of the cargo than the driver. So the driver can go, but the driver is carrying let's say a big truck with a bunch of cars or something, right? Brand new cars. If that goes turtle, then you're going to lose a lot of money, right? Now, we've been over the past several months working with Maruti Suzuki's IDTR. So if you are not aware of this, as we were not aware ourselves before we started this work, IDTR is a set of institutes for driving and traffic research set up by Maruti almost 20 years ago for training drivers for safety, right? And together with what's called the Maruti driving schools, which are many more, they are in various cities and so on, they've trained over 3 million drivers. And the setup they have with IDTR, oh wow. I think, yeah, I don't know what happened. Anyway, This is going to be hard. uh, maybe I can flip it here. Okay, let me not touch it. Sorry. You know, essentially they have a piece of land given by the driver where they've created driving tracks, okay, with signals and road signs and so on. In fact, the way the road looks inside, it doesn't look anywhere outside in India, right? It's a very beautiful world inside with real road markings and all that. And this guy is the driver, or the trainee driver, and this fellow is the instructor who's supposed to be watching him and filling up a report. As you can see, I mean, if you ignore the upside down part, this guy is not really paying attention. It's very hard for this guy to constantly pay attention. He's the instructor, but it's very hard for him to do this job every minute. And at the end of this session, he's supposed to fill out a form like this. Again, you can't read the text, but the form has a bunch of things around observation, like did the driver look at his mirror before executing a turn, for example? Did the driver maintain a safe distance with respect to the vehicle in front and so on? Right? There are a bunch of questions that the instructor is supposed to fill out as part of the test. Our goal is to automate much or all of this. Right? And what we have done initially is we have deployed, the other point, by the way, in IDTR, what they also have is that they have infrastructure sensors. They have external cameras looking down on these vehicles. They have curbside sensors and so on. Obviously you cannot have those in the roads outside. And as I mentioned, if you've only been trained in the IDTR setup, then you're only good to drive in a parking lot in California or something. You cannot drive on any Indian roads, right? So you need to be able to test people on the road, and infrastructure sensors go out of the window then, right? You have to have sensors that you can carry with you, and that's where something like HAMS would help. So, this one didn't get done. I don't know why. This video is just fine. So this is 3 IDTR drivers with our thing running, and unfortunately the text is very light, but this is just gaze tracking. So we decided to pick gaze tracking as the first thing to focus on, in large part because if you think about it, the driver is driving, the instructor is sitting next to him, and the instructor has a very hard time looking at which way this guy's gaze is, right? Other things like speed and distance you can estimate, but gaze is hard. So yeah, this is the thing in action, and so we did this deployment, and it's still ongoing, but this is data from just about 2 weeks of data, where anytime the trainee driver did not scan either mirror for 8 seconds, we generated an event, recorded a short video clip that was then shown to the instructor and also to the driver at the end of the driving session, right? So, and then and this is data from 128 driving sessions. We asked the instructor to rate the clips in terms of usefulness. So on a 5-point scale. So 5 on the scale means that our tool picked out an instance that was really an issue, and the instructor had no awareness of it, right? So if it were not for HAMS, the instructor would not even have noticed it. One is obviously sort of mistakes we made and so on. And so what you see is that we are doing reasonably well. I think about 55% of the time we get a rating of 4 or 5. There are some bad cases that we are working on improving, right? This is fairly sort of early work. And these are some of the sort of video clips that we picked out where for 8 seconds or longer, the driver did not scan their mirrors as part of the training. Yeah. Yes. It's happening local. Yeah, everything is local. Yeah. And that's one of the challenges, right? Because we cannot, for privacy reasons and also for efficiency reasons, we can't be shipping things to the cloud. Now, of course, this is on a lighter note. I was in Shillong a couple of months ago to give a talk, and on the way on the hills, which is sort of fairly winding roads, our driver had stacked up a bunch of bags, so the mirror can't even be seen. So forget mirror scanning in this setting, right? So if you think of safety in India, there's a lot of issues to be solved. I think we are just sort of scratching the surface, maybe, but there are a lot of basic issues that are still to be resolved. So maybe I went fast, but anyway, so this work, as I said, Akshay Nambi, who should be here, I don't know if he's here, he's on the PC of this conference, of this workshop. He has been a key driver of a lot of this work. We have a bunch of students working with us. We're working with Maruti, but we're also collaborating with academia. I mean, not on the specific problems that I talked about here, but as part of the larger project, we're working with IIIT Hyderabad, IIT Bombay, with your advisor, Bhaskar, and with IISc on various aspects. So, we are quite sort of open to working with people. So if you're interested in this space, we are very happy to talk to you. So to conclude, I hope I've convinced you that road safety is a major societal issue. And because of what I mentioned earlier, which is that you need to have more contextual information, both with regard to the state of the driver and what's around the vehicle. Vision, we believe, or camera-based sensing is going to be a key approach to addressing the problem. Now, IoT more broadly, we believe can give visibility into a lot of situations. We talked about driving here with HAMS, but in our lab we have projects around health as well as agriculture, all of which use low-cost sensors to get insight into something that otherwise is opaque. And when you design systems like this, you have to take into account the limitations in terms of cost, connectivity, compute power, and so on, right? And that's where a lot of the challenges lie. Thank you. Yeah.
Hello. So going back to experience of taking a cab in the airport road where this was beeping, you overspeeding, and this guy gets annoyed. And I've seen a lot of instances where these drivers actually will switch off that system off because it's beeping all the time. So the entire purpose of having an alerting system over there is lost. Now, fast forward to a system like CAMS where something's watching you, and as you said, if somebody's watching you, you are conscious about it. But again, we can override that. So where do you see that behavior? How do you think about
but the thing is that, again, I really think this would take off first, assuming it takes off, in a fleet setting, where there is an owner who owns 100 of something or 1,000 of something, and they will insist that the drivers run this, right? If you don't run it, then you'll be out of your job, right? So I think they will, and even in our fleets, in the Microsoft cab fleets where the thing beep, once that happens, they get a phone call. Which actually, I guess, distracts them and makes them less safe for us, but they get a phone call saying, what's going on? Why are you going so fast? So I think in a fleet setting, you can certainly enforce this. On individual basis, even with consumers, you can think of, let's say you have a teenager who started driving. As a parent, you might insist that you have a device like this. You may not be very popular with your kid, but you could insist on that at least until you have confidence that they know how to drive. So I think that's an issue that can be addressed. And insurance, right? That's the other thing. So insurance is already happening with insurance telematics. I don't think they're using cameras, but the same idea could extend to that as well. Okay.
Any other questions?
Yeah.
So it's a fantastic work. So I would like to know about the gaze tracking. So are you considering something like points of interest or regions of interest or areas of interest? Like how do you
essentially, we are getting the facial landmarks.
Okay.
Once you get the facial landmarks, then looking at the geometry of the landmarks you can sort of back calculate. This is standard stuff, the head pose, right? Think about it. If your face is looking directly at the camera, you'll see a completely symmetrical set of landmarks. If the face is turned, then it will be skewed in a certain way. So you can sort of, this is not our work, this is standard way of getting the head pose. For the eye part, what we do is we just we take the landmarks around the eye and just get a patch, image patch around the eye, and just feed that to a DNN for training. We don't actually calculate which way the eye is looking. We just take image patches and feed that to the DNN along with the head pose, and we are able to get the composite.
Great. So I'm as well as very curious to know whether, did you think in terms of eye tracking device like Tobii software or something? So did you think about it?
Yeah, I think you could certainly use those, and those exist. Again, it's a question of deployment and cost and so on, right? So
it's quite expensive.
Devices cost money, plus now drivers will have to start wearing things that...
it's like a wearable and non-wearable as well. Like you have to.
Yeah, I mean, I think at some point down the road, it would make a lot of sense. At this point, I don't think if you want a low-cost, highly deployable
just for
solution,
Indian traffic.
The other thing is, those are, probably good for Vijay's kind of application. Very precise tracking of what you're looking at. What we're trying to do here is sort of more coarse-grained. We just want to know that someone is not just fixated on the road in front, or someone is actually, rubbernecking or something. Right? We don't need to know precisely what their eye gaze is. So therefore, we're able to get away with something.
So the evidence is going to be just like a heat map or something. So
no, it's more than a heat map. So it will be like what I showed, right? So I showed. Let's see if I can go back. Okay, I don't know what happened. I showed an instance where the driver was just looking directly in front, and our system did not detect either a left mirror scan or right mirror scan for 10 seconds. So at that point, we will say, okay, something happened that should not have happened, record a clip, right? And at the end of the session or end of the drive, you can see how often that happened, and even have those video clips so that the driver can see what he or she did.
Thank you, sir.
As well as the configuration of hardware, because you have been saying it's a low-cost device. So would it run on smartphones which are of like,
Yeah, actually,
low cost?
Akshay would be the right person to answer both of those questions because he's really been driving a lot of the technical work. But we are not talking about high-end smartphones here. We are talking about Android devices that are perhaps in the $200, $250 range. Right? So they are not that expensive. With regard to the details of the technical stack, I think offline with Akshay would be the best. Yeah. Yeah. So we are gathering data as part of our data thing.